Hello and welcome to today's lesson on quantum physics. Today we'll be covering some exam questions. I'll be going through the working out of some exam questions on photons. So question number one is a multiple choice question, and it's asking which is not the unit of energy. Okay, so if we go through all of these possible choices of units of energy. Okay, so the first one is kilowatt hour. Now we know that kilowatt hour is, kilowatt is power and hour is time. So power times time gives us energy. So the first one, A, is indeed a unit of energy. The second one is also a unit of energy that we learned about during the sessions. It's for very, very small values of joules, much less than 1 joule. We use the unit of energy electron volts. And as we know, C is also a unit of energy, joules. Watts is the unit of power, so D is the correct answer. Question number two, another multiple choice question. The total energy gained by 20 electrons traveling through a potential difference V is given as 30 kilo electron volts. What is the potential difference V? Okay, so there is an equation that we can use to work this out. Okay, and that is energy in electron volts is equal to the number of electrons multiplied by the voltage for each electron, or the potential difference for each electron. So we know that the energy is 30,000 electron volts. We know that there are 20 electrons. So if you rearrange to make V the subject of the equation, we are left with 30,000 divided by 20 should give us a potential difference of 1,500. So your answer should be C. Question number three, the minimum potential difference across a light emitting diode LED before it conducts is 2.1 volts. The wavelength of the light emitted by the LED is lambda. E is the elementary charge. C is equal to the speed of light in a vacuum. What is the correct expression for determining the Planck constant H? So we know that the energy EV is equal to Hc over lambda, okay, where V is the threshold voltage. Okay, so if we put in our values into those equations, so we know that E times 2.1 is equal to Hc over lambda. If you rearrange that equation to make Planck's constant the subject of that equation, we are left with 2.1 E lambda divided by C. So that gives us the answer D. Question number four, which of the following statements is or are true about photons? Number one, the speed of a photon changes at the boundary between air and glass. Number two, photons are electrically neutral. Or number three, the energy of a photon depends only on its wavelength. Okay, so going through all of those, light certainly moves more slowly in glass than air. Okay, so it bends towards the normal as it travels into glass, so it's slowing down. So the first statement is indeed correct. Photons are indeed electrically neutral, so the second statement is also correct. And we know that the energy of one photon is equal to Hc over lambda. In other words, the energy of a photon is inversely proportional to the wavelength. So all three statements are correct. So our answer is indeed A. Question number five. A sodium lamp is rated at 40 watts. Only 12% of the power is emitted as yellow light of wavelength 5.9 times 10 to the power minus 7 meters. How many photons of yellow light are emitted per second from this lamp? Okay, so First thing we need to do is we need to work out the energy of each photon, which is given by the equation hc over lambda. So we are given the wavelength of yellow light, we know Planck's constant, and we also know the speed of light in a vacuum. Okay, so we can plug those numbers in. 6.63 times 10 to the power minus 34 times 3.00 times 10 to the power 8 divided by 5.9 times 10 to the power minus 7 gives us 3.37 times 10 to the power minus 19 joules. Okay, now we need to work out what is 12% of 40 watts, which is the power emitted by yellow light. And that gives us 4.8 watts, which is equal to 4.8 joules per second. So the number of photons per second is equal to 4.8 joules per second divided by 3.37 times 10 to the power minus 19 joules, okay, which gives us 1.4 times 10 to the power 19 photons per second. Okay, so that tells us that the answer is A. Now there is a formula as well that we can use to work out the number of photons per second. Okay, it's given by the equation there that I've written in blue. The rate of energy transfer, or the power, is equal to the number of photons per second multiplied by the energy of each photon. So we can rearrange that equation, and that tells us that the number of photons per second is equal to the rate of energy transfer, okay, divided by the energy of each individual photon. Okay, and that tells you how many photons are being emitted every second. Okay, so the answer is A. Question number 12. What is a reasonable estimate for the energy of a photon of visible light? Okay, now we need to have an idea of what is an estimate for the wavelength of visible light. Okay, and the wavelength of visible light is approximately 5 times 10 to the power minus 7 meters. Knowing that, we can then plug that into our energy of a photon equation. So E is equal to hc over lambda gives us E is equal to 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8, and then divide all of that by the wavelength of visible light, 5 times 10 to the power minus 7, which gives us 4 times 10 to the power minus 19 joules. So our answer is A. Question number 13. Which of the following values is typical for the wavelength of visible light? Okay, so just in question number 12, we should know that the typical wavelength of visible light is about 5 times 10 to the power minus 7 meters. So the answer to the first part of that question is B. Okay. Use your answer to determine how many photons of visible light would be needed to produce an energy of 4.2 joules. So first of all, we've got to work out the energy of a single photon. So we will use our famous equation for that, which is energy of one photon of light of this wavelength is given by E is equal to hc over lambda, which is equal to 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8, and divide all of that by 5 times 10 to the power minus 7, which gives us the energy of one photon of visible light as 3.978 times 10 to the power minus 19 joules. So we know that one photon gives us that amount of energy. X number of photons will give us 4.2 joules of energy. Okay, so we know our equation, which is the rate of energy transfer is equal to the number of photons per second multiplied by the energy of each individual photon. Okay, so if we rearrange that equation, then we can find the number of photons in 4.2 joules of energy. So we do 4.2 divided by 3.978 times 10 to the power minus 19, which gives us 1.1 times 10 to the power 19 photons. Okay. So here we have question number 14, which is a 3-mark question. The wavelength of light from the LED is 480 nanometers. The radiant power emitted from the LED is 1.2 milliwatts. Calculate the number of photons N emitted from the LED every second. Okay, so we know that the LED has a wavelength of 480 times 10 to the power minus 9 meters. Okay, that's just converting the 480 nanometers into meters. The power is given as 1.2 milliwatts, which is equal to 1.2 times 10 to the power minus 3 joules per second. The energy of each photon is given by E is equal to hc over lambda. So E is equal to 6.63 times 10 to the power minus 34 times 3 times 10 to the power of 8. Divide all of that by the wavelength, okay, which is 480 times 10 to the power minus 19. We get 4.14 times 10 to the power minus 19 joules. So the number of photons per second is equal to 1.2 times 10 to the power minus 3, okay. Divide all of that by 4.14 times 10 to the power minus 19, and we get 2.9 times 10 to the power 15 photons every second. Okay. So again, using that equation, the rate of energy transfer is equal to the number of photons per second multiplied by the energy of each individual photon. Question number 16. Okay, an LED emits light at wavelength 5 times 10 to the power minus 7 meters. A, state what is meant by a photon. So we don't actually need those numbers, the wavelength given there. Okay, the key thing is to know the meaning of what is meant by a photon. So a photon, okay, is a quantum or packet of energy of an electromagnetic wave. Okay, so if you just said a photon is a quantum of energy of an electromagnetic wave, that is absolutely fine. Or you could also just say a photon is a packet of energy of an electromagnetic wave, and you would still get the mark. Okay, part B is the intensity of the light emitted from the LED is doubled. Explain the effect this has on the energy of the photon. Now, when we look at the photoelectric effect, we'll look at this in a little bit more detail. But just to let you know that doubling the intensity of a photon doesn't affect its photon energy, which only changes if the frequency of radiation is increased. Okay, so the greater the intensity just means that there will be more photons incident per unit area per second. Okay, because remember, intensity is power per unit area, and power, as we know, is energy per second. Okay, so a greater intensity just means that there will be more photons incident per unit area per second, but their photon energy will not change. Okay, so intensity will not have an effect on the energy of the photon. Question number 17. Calculate the energy of a photon of frequency 4 times 10 to the power 18 hertz. Okay, so getting plenty of opportunity to use the energy of a photon equation, which is E is equal to hc over lambda, but we also know that E is equal to hf. Okay, so E is equal to the Planck's constant multiplied by the frequency of the given photon. Okay, so we get E is equal to 6.63 times 10 to the power minus 34 multiplied by 4 times 10 to the power 18, which gives us an energy of photon of 2.7 times 10 to the power minus 15 joules. Question 19. In a microwave oven, photons of energy 1.02 times 10 to the power minus 5 electron volts are used to heat food. A. Express 1.02 times 10 to the power minus 5 electron volts in joules. Okay, so as we know, if we're going from electron volts to joules, we have to multiply by 1.6 times 10 to the power minus 19. Okay, so we simply take our value in electron volts, which is 1.02 times 10 to the power minus 5, and multiply that by 1.6 times 10 to the power minus 19, which gives us energy value in joules of 1.63 times 10 to the power minus 24 joules. Okay, part B, calculate the frequency of the photons. We are going to use our famous equation. Energy of a photon is equal to hf. Okay, rearranging that equation to make frequency the subject of it, we have E divided by h is equal to the frequency. So we can say that 1.63 times 10 to the power minus 24 divided by 6.63 times 10 to the power minus 34 gives us 2.46 times 10 to the power 9 hertz. On to part C, calculate the wavelength of the photons. Okay, now we can use our wave equation for this one. C is equal to F times lambda, rearranging to make lambda the wavelength the subject of the equation. We have C over F. So lambda, the wavelength, is equal to 3 times 10 to the power 8 divided by 2.46 times 10 to the power 9, which gives us 0.12 meters. Okay. Question number 22. Procyon is a star of radius 1.4 times 10 to the power 9 meters. The total output power of the electromagnetic radiation from its surface is 2.7 times 10 to the power 27 watts. The average wavelength of the electromagnetic waves from Procyon is 5 times 10 to the power minus 7 meters. Part 1. Show that the surface intensity of the radiation from Procyon is 1.1 times 10 to the power 8 watts per meter squared. Okay, so we know that we're talking about a sphere, okay, which has a radius of 1.4 times 10 to the power 9 meters, okay, and we know that intensity is equal to power divided by area. So in this case, the area we're talking about is the surface area of a sphere. So we can say that the intensity is equal to the power divided by the surface area of the sphere. And we know that the surface area of a sphere is 4 pi r squared. So we can say that I is equal to P over 4 pi r squared. Okay, we've been given the value for the power, so we can put that into our equation, and we also know the radius of the sphere. So intensity is given by 2.7 times 10 to the power 27 divided by 4 pi, multiply that by 1.4 times 10 to the power 9 and square that number. Okay, and we get 1.1 times 10 to the power 19 watts per meter squared. Okay. Now, question 22, part 2, asks us to calculate the energy of a photon of wavelength 5 times 10 to the power minus 7 meters. Okay, so the energy of a photon is again given by E is equal to hc over lambda. So we plug our numbers in, we get 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8. Divide all of that by the wavelength, which is 5 times 10 to the power minus 7, and we get an answer of 4.0 times 10 to the power minus 19 joules. Question number 22, part 3. Estimate the total number of photons emitted per second from the surface of Procyon. Okay, so we can use our equation. The total energy transferred per second is equal to the number of photons per second multiplied by the energy of each photon. Okay, so the total energy transferred per second, that is just the power, which is 2.7 times 10 to the power 27 joules per second, which is equal to the number of photons per second multiplied by the energy of each photon, which is 4 times 10 to the power minus 19 joules. Rearranging that equation to make the number of photons per second the subject of that equation, we have number of photons per second is equal to 2.7 times 10 to the power 27 joules per second. Divide that by 4 times 10 to the power minus 19 joules. We can see that the joules cancel out, and we're left with 6.8 times 10 to the power 45 photons per second. Question number 23. A high energy gamma photon passing through a scintillator crystal Convert some of its energy into visible light photons of mean wavelength 450 nanometers. Show that the energy of a single photon of wavelength 450 nanometers is less than 3 electron volts. Okay, so we can use our energy of a photon equation, E is equal to hc over lambda, which is equal to 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8. Divide that by the wavelength, which is 450 times 10 to the power minus 9 meters. Yes, we've converted the 450 nanometers into meters. Okay, that gives us the energy of a photon as 4.42 times 10 to the power minus 19 joules. Okay, now we have to convert this into electron volts. So we're going from joules to electron volts. That means we have to divide by 1.6 times 10 to the power minus 19. So 4.42 times 10 to the power minus 19 divided by 1.6 times 10 to the power minus 19 gives us 2.76 electron volts, which is indeed less than 3 electron volts. Question number 24. Filament lamps are being replaced by LED lamps in many large organizations. LEDs are low-powered devices. Part 1. Apart from cost, state one major advantage this can have on the environment. Okay, so there are a couple of alternative answers that we could have. The first possible answer is that less energy used from power stations, which in turn produces less carbon dioxide emissions, leading to less environmental damage. Or an alternative to that is we could say that the infrequent need for disposal of LED lamps has less impact on landfill sites or use of natural resources. Okay, so either one of those would have given you 1 mark. For part 2, a light emitting diode emits photons of a specific wavelength. The intensity of the light emitted from the LED is doubled. Explain the effect this has on the energy of a photon. So we've already looked at what the changing the intensity of light has on the energy of a photon, which is none. So we can say that the energy is equal to HF, which is equal to hc over lambda. So we certainly know that the energy is directly proportional to the frequency, and the energy is inversely proportional to the wavelength. Okay, but in terms of the intensity, energy doesn't depend on intensity, therefore the energy of a photon remains the same. Okay, question number 25. The Planck constant H can be measured in an experiment using light-emitting diodes. Each LED used in the experiment emits monochromatic light. The wavelength lambda of the emitted photons is determined during the manufacturing process and is provided by the manufacturer. When the potential difference across the LED reaches a specific minimum value, known as V min, the LED suddenly switches on, emitting photons of light of wavelength lambda. V min and lambda are related by the energy equation, which is just given over there. EV min is equal to hc over lambda. Okay. Discuss how you could use the circuit shown in figure 7.1 to determine accurate values for V min and how data from the table can be used graphically to determine a value for the Planck constant. Okay, so this is we talked about this experiment before, an easy experiment to find the Planck's constant using LEDs. There we have some different types of LEDs with their wavelengths, which is given by the manufacturer, and you have the V min, which is just the same as the threshold voltage. So what we really need to do is just to make sure that we write the steps or the method in which we're going to undertake this practical, and then we've got to write a number of steps where we talk about how we actually find or calculate the Planck's constant from our data. Okay, so the first point we could make is that we can adjust the potential divider to 0 volts. Second point to make is that we connect the flying leads to one of the LEDs. Okay. The third point we can make is that we need to increase the voltage until the LED just lights. Okay, take a recording of that value. Repeat this at least twice more and take an average of the voltage to find the threshold voltage, which is V min. Okay, and that will give us some more accurate reading. Then we repeat the steps for each LED. Okay. Then just to improve our results for better repeatability, we can say that you can shield the LED inside an opaque tube to judge the moment it just lights up more accurately. Okay, so those are all the steps for the method. Okay, then we can look at the working out the Planck's constant from our results. So we can plot a graph of threshold voltage for each LED. Okay, with its V min on the y-axis against the 1 over the wavelength on the x-axis, which we have to work out. Okay, and then we expect a straight line through the origin, so we can extrapolate our graph to the origin, drawing a line of best fit. Then we can work out the gradient m, which is equal to V min multiplied by the wavelength, which is also equal to hc over E. Okay, so if we rearrange that equation, okay, and substitute in V min multiplied by lambda with the gradient m, we are left with h is equal to me divided by c. Okay, now you don't have to write all of those points. You would need to take, perhaps it's worth 6 marks, this question, so you would take 3 points from the method, and you would take 3 points from how you actually go about working out Planck's constant. So, question number 26. Figure 4.1 shows the IV characteristic of a blue light emitting diode, an LED there. So this is quite a similar question to the number 25 in terms of the fact that it's the same experiment where we're using LEDs to help us determine the Planck's constant experimentally. Okay, so we can see the IV characteristic there for current against potential difference. We've got a circuit diagram as well. Okay, so the energy of each photon emitted by the LED comes from an electron passing through the LED. The energy of each blue photon emitted by the LED is 4.1 times 10 to the power minus 19 joules. Calculate the energy of a blue photon in electron volts. Okay, so again, we are converting from joules to electron volts, so we divide by 1.6 times 10 to the power minus 19. So we have 4.1 times 10 to the power minus 19 divided by 1.6 times 10 to the power minus 19 gives us 2.6 electron volts of energy. Part 2 of question 26 is, it says, explain how your answer to part 1 is related to the shape of the curve in figure 1. Okay, so we have to relate it to that particular figure there. So one photon, we know, emits 2.6 electron volts of energy. 1 electron volt is 1 volt, so 2.6 electron volts is 2.6 volts. So looking at that graph, we can actually see that that is approximately the point for V min, the point at which the current begins to flow through the circuit, or the point at which the LED will light up. So we can say that the LED only conducts or allows current to flow above 2.6 volts. An electron must pass through a potential difference of 2.6 to lose energy as a photon of blue light. Okay, and that part there is worth 2 marks.